Hello, welcome, good morning. Is that just in my ears or is it really loud? Okay. Welcome to my talk about the interesting malware. I'm super proud of the title I came up with because it's like, it matches the topic so well. First of all, I'm here with my Linux machine that I'm not having under control like 100%, so this is a Windows VM, and the VM says it's not activated, which is actually not true. I do have a license. It's just that the VM wouldn't recognize my license. Anyway, that's a different problem. So today I'm here to speak about interesting malware to you. And no, I'm really not kidding, that's interesting binaries. And the topic, like the title came up because so many people are ranting about how boring usual Windows malware has become, and that is really true. Like we have masses of malware, and I promise you, most of it is not interesting. So this one is. Again, my name is Marion. I've been here a couple of times. Currently, I work for G-Data Advanced Analytics, which is a company based in Bochum, and does malware analysis. This slide I also designed myself. I'm super proud about the code. I go to seek a grade, perhaps, which is the credo of my work, which is what binary analysts usually do. Many people think that we look at binaries and like find out the ultimate truth because it's zeros and ones, right? It can be nothing about guessing, but usually a lot of my job is putting up hypotheses and proving them or denying them, and in the end having still a long list of guesses which are more or less true or not. Also, binary analysis itself is a lot about digging in other people's underwear. I found out because the more interesting, the more popular a piece of malware is, the more embarrassing it is for the people who wrote it when you take it apart. It happened so in the past. But then, just recently, a friend pointed out that we're actually not that much digging around in dirt, but what we do is we criticize art. So there is less interesting binaries and there's more interesting binaries. And the more interesting ones are actually art that have been built by software developers. The binaries I'm going to be speaking about today, I actually started working on with a friend of mine, who I wanted to credit at this point. Some of you might have heard about him. His name is Morgan. He's like really good at digging up interesting binaries. And thanks to him, I got my hands on a couple of binaries that we named Cheshire Cat. This picture should represent the wonderland that Alice was lost in, where Cheshire Cat was walking around. Because Cheshire Cat is kind of the spirit animal of these crazy binaries. Altogether, oh, come on, yeah. Altogether, the set of binaries consists of 5 malware pieces. The interesting, or the at first sight interesting part about these binaries is that the oldest one of them has been compiled more than 10 years ago, like in 2002. And the newest one that we found in 2011, which makes a time span of about 9 years. This is a very long time to write one specific family of malwares. This is actually one of the, well, if you call it an operation, one of the longest running operations that have been witnessed, and one of the operations that's reaching back in time the farthest. But also, if you look at these timestamps very closely, there's 2 in there from 2007 and 2008, which date on the same day. This usually is an indicator that people have forged timestamps on their binaries, so I wouldn't take these compile stamps as fully trustworthy. But what is interesting about these binaries is that although the timestamps might be forged, they have indeed been written for very old operating systems. I will tell you about this in a minute. So let's take a look at the first of this interesting set of binaries. Compiled in 2002, but actually targeting platforms that are far older. Back in the days when the Pet Shop Boys were still a thing and people were still playing Minesweeper. Old is gold. The implant from 2002 was designed to interact with a driver installed on the infected machine, sending IOCTLs to a device named ASR2892. This is actually about this functionality most that we could find out, so we never got our hands on the driver, which is this control component. Furthermore, this component would act as a harness, so it would search for security products installed on the infected machine. If you now have a look at these security products, I'm not sure they don't look like modern day antivirus and firewalls. What you find in there is software like the AT Guard security guard and the Zone Alarm firewall and Etherreal as a network monitoring tool, which I think was abolished years ago before I even started using sniffers. So the tools being searched for are also from back in the days. Furthermore, the binary would drop an executable, a 4 kilobyte executable, which would be used to spawn other processes. So dropping that binary, redirecting the input handles and spawning a third-party process would mean that the execution harness would still have control over the executed binary. This while it was able to protect this executed process from other security products installed on the system. An interesting point about this, this dropping mechanism was that it would check the PE header of the third-party executable it would start, would search for the PE header, but also check whether it had a valid NE header. Now, I, in my short analyst life, have never heard of NE before. Googled that and found out it's the new executable header, which was there before PE was even a thing on systems. Also interesting about the binary was that there was a load of strings in there. One of them saying something like running this kind of application is forbidden because 16-bit or DOS on a non-9x platform are forbidden. Furthermore, when looking into the new executable binary format, one would find out that it was used on Windows 1.0 to 3.x and on multitasking MS-DOS 4.0 platforms. So this was a long time before I started to analyze, and also some time before 2002 when the binary supposedly was compiled. So from this first implant, we can say that the family we're looking at are targeting like super old platforms. All right, let's go on. There's some more binaries that we're going to look at, and these implants were compiled supposedly 2007 to 2011. These implants were somewhat different from the first one, but the four that fall into this group were all very similar, so they all followed the same objectives and just developed over time, which we'll also be talking about later. And this development looked like. Basically, what the implants did were espionage, covered as icon handlers on the machine, and they did that very carefully. Like they were very carefully to not be detected and to not catch any attention on the infected system. Now, what is an, here's my Cheshire cat again. A true implant, what is an icon handler? An icon handler on Windows is actually an extension for the Windows shell, which basically means a plugin for the Windows Explorer as we see today. Like an icon handler can be installed to manage the loading of icons for specific file types. In this case here, the binaries will be an icon handler for link files, which technically means whenever Windows Explorer loads a link file and loads an icon for that link file, this handler would be invoked. This happens every time someone loads the desktop, which basically is whenever a user logs onto the Windows machine. The shell, in our case, or in the case of these binaries, was the program manager, because apparently when they were written, the Windows Explorer wasn't yet a thing, so the binaries really look for the progman.exe. They are registered as COM servers, which means they serve their functionality as COM objects at runtime, and the objects in the end perform the actual work of the malware. A very nice definition of what a shell extension actually is was written by Michael Dunn. Shell extensions are really COM objects that add some kind of functionality to the Windows Explorer. That said, shell extensions really can do anything, so it doesn't need to have anything to do with the actual icon that's being loaded, but you can really hide the entire malware within the icon handler and not having anything to do with the actual icon. Furthermore, it can be said that these icon handlers were written in C, kind of, but not really, but really C, that looked like C++, or that wanted to look like C++, which is curious because usually you don't write shell extensions or icon handlers in C. Another guy on Stack Overflow mentioned that this could be noticed as a violation of the Geneva Convention on Programmers' Rights in most jurisdictions. So yeah, the binaries are actually written by someone who knows C very well, but try to emulate functionality from C++. So you wouldn't find C++ structures within these binaries, but you would find objects that were like implemented as structures and memory structures that were used like C++ objects. I'll also be talking about this in a minute. Before, all right, like the implementation of the icon handler, of course, before you can be loaded as an icon handler, you should delete the icon cache, otherwise the icons are not reloaded. And then how this works is the binary has to be installed as an in-process server, which means a COM server, which later on can handle the objects that are being served by the server. This works with the listed registry keys. So in the first step, the malicious DLL has to be registered as the server, and later on, the icon handler can serve the malicious or the malware objects via the identification class ID. The implant is not only stealthy, it's also a very sensitive implant. Here I try to sketch out my reverse engineering process on the one single function that would try to determine the Windows operating system it was running on, which is rather sketchy. I'm not kidding, this function was huge and tried to find all the details about the installed operating system. This basically boils down to a function that determines which operating system and which line of Windows operating systems is installed on the machine. Where in most cases, the malware would want to know whether it's a Win32 Windows or a Win32 NT platform, which makes a major difference, or made a major difference, like 10 years ago, within the Windows 32 API and the API calls that were actually available on the systems back then. But furthermore, the function would find out the specifics about the operating system and the patch level that was installed. This information throughout execution will be used to determine which functions to call in the run, because a lot of functionality within these binaries will be implemented redundantly. So you will have, for example, one function which treated the Windows NT line and one function which treated the Win32 Windows line, which resulted in a lot of redundant code within this binary. As mentioned, they would do very fine-grained version detection and lead to a lot of interesting old-school Windows code within that binary. One example for that is the process enumeration that is implemented within the malware. We really have this very simple handler, where in the beginning you can see there is the check of the Windows operating system, where it determined whether it's Windows NT or the Win32 Windows line of Windows. And you can see that for the non-Windows NT line, it would use the usual APIs that malware analysts know to help in enumerating processes, which is the toolhub 32 snapshot and process 32 first and process 32 next, which is the usual APIs that one would expect. And on the upper part of the screen, you can see how old Windows operating systems would perform this very same task, which is namely work with the CW Query System Information API. That was back in the days when these NT wrappers were not created yet. The API that would be used to enumerate processes on a Windows platform. This API delivers the system process information structure, and within there you can find a pointer, a linked list between all the running processes on the system and gather the names from the processes. As usual, Microsoft put online a very great documentation for this kind of API, where you can see a lot of the values in there are reserved. But I can tell you at the offset 70, within that structure you will find the actual process name of the process you're looking at. With this list, the malware would iterate through the running processes and gather the names of the running processes. All right, this habit of adapting to different operating systems can be seen throughout all of the binaries. So someone put a lot of effort into adapting his binary to the different operating system versions. What was also very interesting was that the whole binary was written in a very strangely unstructured manner. So when I looked at the binaries, I had a feeling like I could have written them, kind of, because what the developers did was basically just stacking functionality on top of each other. I'm not a software developer. When I write software, I like punch it together and copy paste from Stack Overflow and like make it run. And although I'm sure these people didn't have Stack Overflow available when they wrote the binaries, they kind of did the same thing. They called functions whenever they felt like they had to call the functions. There is no visible software design in there, except for one piece of functionality, which is the C2 communication. How to C2 now describes how the communication from the machine to the remote server is implemented. So there, basically, the malware will go to ARM, a communication object, I call it, which contains the domain to be contacted, the data that should be communicated to the C2 server, the file name, if the file is involved, to be sent or to be downloaded, and a lot of timeout values. And on the other hand, we'll have a communication handler, which in the binary is totally detached from the actual communication object, where the handler would then build the connection to the C2 server and send and receive data. This communication handler will be injected into a default browser that is installed on the system. This is something that we also see in common malware today. What we barely ever see in common malware today is that the malware would disable the remote administration service before the communication process and re-enable it afterwards. I did a lot of Googling, but I couldn't quite find out how RAS would disturb the browser injection and the execution from code within the browser, but apparently back in the days that was a problem. The communication object would be transferred to the communication handler through a pipe, and from there the communication through the default browser would be performed. What is interesting though is that this functionality isn't centralized sort of within the binary, but is called whenever the people who wrote the binary felt like calling that API, which again gives me the feeling that there was no particular software designer involved in the process. Again, for this browser injection process, we see two different implementations, which I will now explain in detail. So we had the sort of classical style injection, where the malware would create practically a remote process within the browser executable browser process. It didn't do this in a totally normal way though, because nothing in this binary is implemented in a totally normal way. It will, for example, gather the API for a load library, not by calling it proc address, but for searching for the offset of load library within its own process. So for loading this API, it will search its own process space for the load library routine. Then we'll create a browser instance in suspended mode, as we know it, and we'll go on to then load its own library in the process of the suspended browser. This will be performed in the way that it would allocate memory within the process space of the suspended browser and write its file name there, and then search for the load library function within the remote process to load this string, technically, like this library, within the other process. Then load it within the remote process. It would write the communication object I described before to the suspended process and invoke the communication handler I described before within the suspended browser process. And this will then run as a remote thread. This is sort of like what we see today. Now the retro version of this browser injection works a bit different and makes use of less Win32 APIs. Namely, in this process, the malware would first craft a bigger data structure. This data structure consists of a set of APIs that would use later. It would consist of a piece of shellcode, which would then later on be used to create the thread within the browser process. It would again contain the communication object I just described. And it would contain a marker, which would later on be used to find the entry point of the shellcode to override that address. Again, a suspended browser process is created, and then the malware would write the entire data structure to the remote process, override the entry point, and technically replace the code within the suspended browser with its shellcode. It would then search for the offset of the shellcode to patch the entry point, and then just resume the suspended process. The suspended process then would load the shellcode that was just written to its entry point, which would then load the malware library to the process, and again invoke the communication handler with a pointer to the communication object. It sounds a bit more simple than the other process before, but in fact this is all implemented without using the classical Win32 APIs, which we nowadays know for process injection. The C2 communication overall would use about 6 to 10 hard-coded domain names, 6 in the older versions, 10 domain names in the newer versions. I've pasted some examples here, and these domains would be referenced by an index number. So technically, within the binary, you do not really see the strings, but you always see the reference index number. This domain is handled by the communication object, which is technically a structure, but not really an object, but kind of an object. And it would be dictated by the index number. Communication with the C2 would mainly happen as the HTTP query string content. So when the binary would run, you would see the content of what the malware wanted to communicate as an obfuscated string within the HTTP query. Another interesting point about the domains, though, these were singled by Kaspersky around 2009. So apparently, around 2009, Kaspersky has already been analyzing these binaries. Keylogging. Finally, I get to the actual functionality. So what you've seen before was like still the structure around the binary. The keylogging is one of the things that I could determine the binary is actually intending to do as a malicious action on the machine. This would work with a global Windows hook. A global Windows hook is a functionality in Windows which allows you to load DLLs or to load your custom code into processes running on the Windows desktop. So with the global Windows hook, you can actually load your malware into all desktop processes. There, our malware would filter for Windows messages, for window messages. Thereof, it would search for the key first, and this is key down message, which technically is any keystroke or any system key that is being used on the keyboard. I will then go on to craft a structure within the remote process where the keylogging was happening. Craft a structure with a specific identifier, and also craft it with a handle to the window where the keystroke was captured, and the actual key text or the translated code of the keystroke that was being captured. Then I will go on to translate the system keys to specific codes and also store them in the object. And write all of that to a view. On the other side, the malware binary that was still running would watch out for that view and parse the data that it would receive. I would find the keystrokes identified by the mentioned identifier, and also fetch the name of the window that was associated with the window handle that was stored within that object. They would then write all the data to a temp file. This way the keylogger would know which window has received which keystroke and structure the temp file accordingly to get the keystrokes which refer to specific windows. Interestingly, at that point, the temp files that the malware would write, their names would start with a tilde and a D and an F, just to mention that at some point. Another functionality that I personally found was the file system enumeration. So the malware will go on and enumerate the file system, like other malwares do today as well, and gather information about specific files it would find in the file system. It would enumerate fixed drives and walk the entire file system that it could find. And interesting on this functionality was that strings being used within that function were being so the strings within the binary were decrypted at runtime and would only be decrypted for their specific use. So whenever an API needed one of the hard-coded strings, the string would be decrypted, the API would be called with the decrypted string, and later on the string in memory would be encrypted again. So at runtime, it's very unlikely to find clear text strings that the malware was going to use. Again, the file system enumeration was implemented for different versions of Windows. The new version would use the find first file, find next file, and find close APIs that we know from malware today. And the retro version would use COM. Malware analysts in the room will know that COM is a nightmare. COM stands for the Component Object Model, which is a splendid invention that Microsoft had, where you can instrument the Windows operating system through the component object model, which means that technically you can access Windows functionality through abstract objects that you can request from the operating system, and these objects will then provide the functionality that usually the Windows 32 API provides. How does it look like? Here you can see code which is probably one of the best documentations that you can find about these component object model objects that Microsoft provides. I grabbed this from the Wine implementation, and it describes the iShellink object. So here on top you can see the class ID, which is the identifier of this specific object, and here you can see the vtable, which describes the object and how it will later look in memory. So you can see this can be quite hard. If you see a COM object being retrieved from the operating system, which would kind of like look like this, to find out which functions are actually called in the end. This is all implemented with the co-create instance API, where you can retrieve an object associated with a specific class ID. And this object afterwards serves you the functionality which is provided by this specific class. In the end, in the binary, you see API calls that look kind of like what is listed down here. You have a pointer to the object you just instantiated and an offset which points to the specific member function. But it is not a short way to find out which function is actually called within the binary. All right, all that about the functionality. Let me get to the execution flow. So one of the most challenging parts of these binaries was, as mentioned before, they're not structured. You don't go and analyze a specific function and then see in which context this function is being called and where it pops up. But you have to go like my function, my function, my function. And it's just really hard to find out how they relate together. This is also because the authors put some special effort into obfuscating their execution flow, which I will list on this slide. So first of all, the binaries would watch out for a terminal services notification to launch their malicious activity. A terminal services notification isn't used often anymore on modern operating system. I think it has been deprecated at some point. But on Windows XP and downwards, this is still a thing. A terminal service notification can notify a running process about a Windows user logging onto the system. So this would be the point where the malware would start its malicious activity. Furthermore, the binary will be structured in function arrays. So after the launch and after setup of the malware, execution will be deferred to function arrays, which would then execute the initialization, the setup, and the actual functionality. I will talk about that in a second. Configuration data of the malware will be stored in queues. So a lot of configuration data is statically stored within the binary as lists and arrays, will then be loaded at runtime and be dumped into queues, which will later serve the configuration data to functions. A lot of the configuration data is not indicated by strings or with any descriptions, which will tell you which configuration data that is parsed, but it would in fact be very hard to find out what the configuration data would actually be supposed to serve. The OS version determination, as mentioned before, is spread throughout the whole binary. So with this determination, the binary would decide which execution path to take in the future, and this also makes distorts the binary further. So the following of the execution path is really hard. Also, it would make heavy use of the registry and store runtime data within the registry and load it again at later points with an execution, which makes it very hard to statically follow which data is stored there and when it is used. And virtual machine stuck. Yeah, anyway, on the next slide, when it finally loads, I will explain further about the function arrays I just mentioned, this one here. So the function arrays that I mentioned are actually really just lists within the binary. You will have large lists of function offsets stored within the executable, which one would suppose are addressed directly, but they're actually not. They are iterated. In fact, the malware has several functions which iterate through this list and find their specific array of functions. So one iteration, for example, would go from an offset and just always jump 3 bytes further in the hope of finally hitting a function offset. That's very interesting, because like binary people, we would expect there to be a 2 or a 4 or an 8 or a 16. But this binary used a 3, which actually means that only every 4th memory offset will be hit, and all of the other jumps like go into the dark. They don't find any valid offset, which in the end leads to a very distorted array. So the arrays that I've been talking about are actually hidden within that list. There's 3 of them, and they're iterated from different directions. So we would have one iteration which started from the top, and would go down by 3 bytes every time, until it found all the initialization functions. There would be another iteration which would start some bytes further up the top and would also iterate by 3 bytes down, and would find the setup array. And also there would be a tear down array which would start from the bottom and iterate its way up by 3 bytes every time. This is the setup function array, as I call it. Here's the Cheshire cat again, because when analyzing that, I felt like that stupid cat. And there's another array which does the same thing with an iteration of 7 bytes, which is also not 4 or 8 or anything we would expect. This other array, though, had a different purpose, namely it would serve the actual functionality of the binary. There would see a structure of 2 function offsets each, indicated by an index. So you can see that you have a 2 up there on top, and afterwards there was a 3, and then there was a B and a C. That's the index numbers for the specific functionalities. Then these functionalities would have an init handler where all the data structures were initialized and the handlers were opened. And then you would have the actual action function where the intended functionality was loaded. At the same time, the arguments for the specific functions would be served out of the queues I mentioned before that were initialized within the init handlers. So within the action functions, one would only find an access to a queue where some random numeric configuration value would be retrieved to then serve as the configuration of that specific function. And here is that stupid cat again, because this was a bit more crazy than the other function arrays before. At this point, I would like to show this quote from Lewis Carroll. It would be so nice if something made sense for a change. Within the binary and within the function handlers, I altogether spent about 3 months to just try to figure out which configuration value would belong to which function and what would it, in the end, invoke within their respective handlers. Also, our malware is being sneaky. It doesn't only try to hide as an icon handler and try to hide its C2 communication very well. It also tries to hide from security products that were installed on the system. Specifically, it will try to hide from antivirus, but unlike the usual malware I'm looking at, it would only try to hide from one specific antivirus. It would, for example, search for the avp.exe process. If you have looked at malware before, that refers to the Kaspersky antivirus product. It would also check whether any Kaspersky version was installed, if any, and would then see if the behavior blocker or the parental control of Kaspersky were installed and activated. Later on, it would adapt its functionality based on the information that this antivirus check would retrieve. So it would see, is the Kaspersky behavior blocker active? And if it's active, I should probably not start the keylogging component. and so on and so forth. The different Kaspersky versions were mapped as a structure within the binaries. You would again have like a beautiful array with indexes, and within there you would find all the registry keys and values associated with the specific Kaspersky versions. And as mentioned, there would be a consistent search. So throughout execution, you see a lot of checks for operating system and checks for the installed Kaspersky version, and also checks for other installed firewall products and security solutions. Come at me, bro. If someone's interested, I pasted all the registry keys from the different Kaspersky version on the slide if someone maybe wants to use them in the future, or I don't know. It also did more evasion, so it would, for example, see whether there were any execution restrictions within the security policies of the running systems that would prevent DLLs from being executed. If that was the case, it would not try to load further DLLs. And also, as mentioned, it would search for other security products, which, if you look through that list, are again not the most up-to-date security products anymore, and would mainly focus on detecting keyloggers. So most of the products listed here have special functionality to detect keylogging and detect the specific hooking that the malware performs. And as mentioned, if one of these products, one of these processes is found running in the system, the malware would not stop running, would go on running, but would decide to not install its keylogger component. Which I thought was actually rather quite smart, because the malware you usually see today, it has security checks on the startup. Like first there's a runtime packer, then there's some security checks like, is there antivirus, is there a virtual machine running on, is there anything awkward? And if so, most malware just stops running. Most of them don't have like a fine-grained decision-making, what they should perform and what not if specific security products are installed on the system. Of course, you have more evasion. There's more searching for products that would scan the network traffic. So the main focus of evasion was one on the keylogger and B on evasion of network capturing tools, which kind of points you in the direction that that was the main purpose of the malware, logging keystrokes and sending out the data. It was logging through the keystrokes out of the network. But altogether, if you think about the general keylogger, that could be done a lot simpler. That could be done a lot less software engineering to just implement a random keylogger that you could install on a system and that would send out data from the network. All right. One of the last things that was interesting about the evasion was that the data that the malware would store within the registry at runtime would be obfuscated when the Kaspersky security product was installed. This is some functionality that was not present in the older binaries from 2007, but was added in the binaries from 2011. Which kind of gives you a hint that Kaspersky probably came up with a signature or some kind of detection for the data that the malware would write into registry, and that the authors of the malware then realized that they should probably hide their registry data from the plain sight of Kaspersky, and then they started to obfuscate it. Curiouser and curiouser cried Alice. So let me recap what I just told you. The binaries are written in C++, but actually want to be are written in C, but actually are aiming to be C++. There are structures in there being used, like objects, but aren't really objects. If you look at objects within a C++ binary, usually you find memory structures that tell you how the object is supposed to look like. That's called vtables. If you have a vtable, you are somewhat able to link some object that is being instantiated within a function and find out which member functions are those that are being called in the course of the execution. With this binary, this was not possible because as the objects weren't actually objects, these memory structures were not there. So they would just be armed as structures and later on be used as objects. But without the memory structures pointing you to a table of which function belonged to which object, it was very hard to actually follow down which functions were called at runtime. Also, the binary looks obfuscated, but it isn't really obfuscated. The only thing that I found that is intentional obfuscation is the function arrays that are being called in a very, very strange iteration. But the rest of the code is really just awkwardly written. It's not beautiful plain C code, not beautiful plain x86 code, but certainly something that that was written by authors who knew how to use x86 themselves. So I talked about this with a friend who's a software developer and who has been developing software for quite a time. And he said what I described looks like someone wrote this binary not in usual C, but large parts of it in x86 assembly. Also, there's a lot of code within these binaries, where again we have a keylogger that writes keystrokes to a temp file that sends it to a C2 server. But the binary actually supports a lot more functions that at first looked like dead code. So I was suspecting to find a lot of dead functionality in there that just serves a confusion purpose. But in the end, for all of the seemingly dead code, I found some kind of link back to the main execution flow. So all of the dead code that looked dead before turned out to be not that dead, which is very confusing. And again, there is no neat module separation, which makes the whole thing just really ugly. Oops. And here we have the big picture sketch, so I tried to outline how the whole binary execution flow works. You can see on top there is straight arrows, because this is what I'm sure of. There's like the setup routine that installs the icon handler and installs the log on monitor to see when the user logs on, and then invokes the setup and initialization function arrays, and from there things go sideways. So somehow execution is deferred to the control function array, and from there the keylogger is invoked, and the enumeration of the file system. And also one functionality that is sort of a dead end. So the DLL has functionality to load another DLL and invoke specific exports of that DLL, but as I don't have the DLL, I can't really tell what this is supposed to do. In the end of my analysis process, I went on to compare the different versions of the executables as I had, because as mentioned, the old versions do not have any evasion from Kaspersky security products, and the newer versions do. And it turns out that there is indeed about a 10% difference between these two binaries, and that's exactly the functions that deal with the Kaspersky product enumeration and the checks whether Kaspersky products are running on the system. So you could really see that the binaries were developed over time. So the first binaries were written at a point where Kaspersky did not yet know about that malware. Then apparently Kaspersky found out about that malware, and the malware authors adapted to this Kaspersky knowledge to hide their binaries again from their detection. Finally, what did we learn from these binaries? So on the one side, we have targets with presumably interesting data, because they were worth that someone designed this crazy piece of malware for them, or for probably a limited number of targets. They should also probably update their operating systems at some point. They're interesting enough to have rather cool malware dedicated to them. So whatever happens in their operation or on their machines is worth writing a smart keylogger for them, and also rather show their Kaspersky customers. On the other side, what do we know about the offender? They probably got money, they probably got time, and they probably got programmers with mad skills on really old Windows platforms. They also have really crazy software designer. So whoever laid out that binary did not have the intention of making it maintainable and scalable and like giving other developers later on the opportunity to develop further. And also they know Kaspersky products rather quite well. I would presume that's somewhere borderline illegal, given all the detailed information you had about the Kaspersky products. All right. If my virtual machine doesn't die right now. I think that was about it with the talk anyway. Soon there should be the last slide coming up. And I thank you very much for your attention. If you have any questions, I'm happy to answer them now.